Okay, great. Welcome. And yeah, as usual, let's start by going through each part. And if you have any questions, stop me and yeah, ask it either in the chat or you can open your mic to ask. And yeah, we'll go through your questions. If not, we'll go through the entire thing and then maybe go through some of the more interesting parts or parts that are a little bit more complex. So without further ado, let's go. Chapter 8. So let's start from 8.1. Any questions you have got when going through this? Okay, I suppose there's no questions. You can still write in the questions in the chat afterwards when you think about it. Let's go through chapter 2. So Graph 16 protocol is the main topic for today. Um, any questions? Setup phase, prover phase. Verification phase, proof simulation. Okay, so that's a very quick run through. Um, okay, so I'll go through some of the parts that I think are quite interesting. So, again, ask questions if you have any. Yeah, it's meant to be a study group and all. So yeah. Anyways, so yeah, proof systems. Let's talk a little bit about proof systems. So, essentially, proof systems are systems that allow you to generate some zero knowledge proofs. In this case, right? It allows you to. So usually it involves a prover and a verifier, and there's an exchange of message, and this exchange of message usually involves you or like the prover wanting to prove something and generating a proof for the verifier, which then verifies it using the cryptographic primitives we introduced in this book. But yeah, um, there is like a more formal explanation of this, which is this. So let sigma be an alphabet and L be a formal language defined over sigma. There is then a proof system language. L is a pair of probabilistic interactive algorithm. PV, prover verifier. Yeah. So that's is what it is, right? And usually we want completeness, soundness, and of course zero knowledgeness in this case. And I believe we briefly went through what those are in the first session. But yeah, so yeah, completeness, if the word is in the language for both prover and verifier, verifier accepts. If the string is not a word in language and verifier follows the protocol, verifier puts reject. And in zero knowledge, verifier learns nothing about X other than X is, so in this case, X is some word other than X is in the language set L, right? And so, yeah, there's also the difference of non-interactive and interactive. And usually we'll talk about a lot of ZKP as we'll refer to a lot of ZKP in a lot of the proofs, a lot of ZKP protocols actually, a lot of proof systems actually are succinct. Um, ZK-Snarks stands for zero knowledge succinct and non-interactive argument of knowledge. That's why a lot of them is succinct when we call them snarks. Yeah, that's where it comes from. That's also why a lot of the modern protocol uses ZKP as a way of compressing data. You see this a lot in rollups and all. Yeah. So yeah, here we go through a little bit of what prover and verifier algorithms are. And yeah, that's it. That's it generally what proof systems is. In a proof system, there's a prover, there's a verifier, and prover wants to prove something, verifier wants to verify something. Both wants to make sure each other are doing the right thing, essentially. That's essentially CKPs. Questions? I suppose not. Let's go to 8.2, Graph 16. So in Graph 16, I'll go through a few parts. Again, please, if you have any question when going through this, speak up. Anyways, so Graph 16, well, first of all, we need to understand Graph 16 to set up this proof system. So Graph 16 is a proof system, and it's built upon well, it depends on the implementation, but it's built upon pairing-based cryptography, and it uses I forgot the curve it uses, but yeah, it uses pairing-friendly curves, and it requires a trust setup. It's not trustless, essentially. Um, so yeah, that's that's what Graph 16 is. It's one of the earliest proof systems out there. Circom uses Graph 16 by default. They also support Plonk, which is like a newer version of proof system. So we'll talk about later. But yeah, so Graph 16, um, when we set it up, we require something called a trusted setup. We'll talk about it in more detail later. But yeah, so let's talk about it. So Graph 16, recall we have something called rank 1 constraint system and R1CS, right? So R1CS is essentially um, something defined over that we talk about when we talk about circuits, when we talk about representing the program in circuits itself. So RNCS allows us to convert programs into well, essentially polynomials. And then we'll also use this RNCS to generate something called QAP, which we can then use to essentially well, it's better used in proof system itself. So QAP are a polynomial that represent or that encodes what we have in our NCS. It's in a way it's the interpolated form. You usually do a Lagrange interpolation on your RICS and then you get the QAP of that application. Both of them are a form, or like they are essentially your application into like converted into polynomial, right? We convert it to RCS first, and then we convert the RCS into a QAP, which we can then use for our next step, which is ZKP generation. So Graph 16, Rob, there is a few parameters we need to in a Graph 16 protocol. Here it is. So R, G1, G2, E, G1, G2, small g, small g, right? So here, R is just the order of the field that of the group, essentially. So this is affected by your elliptic curve, obviously, right? But these two are the finite groups. So G1, G2 are two different finite groups of order R. This is a pairing, bilinear pairing, computable between G1 and G2. So here, GE, G1, G2 mapping to G2, or mapping G1 and G2, mapping G1 to G2, essentially. Mapping G1 and G2 into GT, sorry. Yeah. So essentially, it's a non-degenerate bilinear pairing for some target group GT that G1 and G2 will map to. This is what E is, pairing. Okay. G1, G2 here are just generator for the G1 group and the G2 group. So this is what we need in order to start using Graph 16. And so in the Graph 16 protocol, there's multiple steps. The setup phase, the approval phase, verification phase, and the simulation phase. Simulation phase is mainly for us to reason about if I'm not wrong, the soundness of the protocol. You basically use this to show that to a certain extent to show that without the secrets you cannot generate a false proof. You cannot generate a fake proof. Yeah. Yeah. So in production or like in actual use case, usually we'll look at these three phases: setup, prover, and verification. There's an example here for the R1 factorization problem, where essentially they provide the variables here. And yeah, this is essentially it, right? Order of 13, G1 13, G2 13, E, the pairing itself. This is G1 generator for G1 13, this is generator for G2 13. Yeah, that's essentially it. Okay, so setup phase. So setup phase is one of the more important phase in any in any proof systems that require a trusted setup. And in this specific case, so in the case of Graph 16, note that we need to generate, or like we need to have a setup for every or here it says for every RNCS systems, right? That means for every program, you need to do a setup phase. There is a need to emphasize this because it means that every time you write a new program, you need to do setup. And setup usually is a very expensive step because it requires you, okay, it's not expensive, so to say. It's expensive because we usually use MPC, multi-party computation, but it's usually a very trusted or a very critical step to ensure the safety of your protocol. So there's a need to emphasize this because in a real life scenario, what this means is every time you write a new program, you need to do a setup, and every time you do a setup, you need to take care to not fuck up. Forgive my language, but yeah. So yeah, and a lot of modern proof systems, they either go about fixing this. Actually, a lot of the new ones, new proof systems, actually come about to resolve the problem of this circuit required circuit trusted setup, right? Per circuit trusted setup or per program trusted setup. What they do is they have something called a universal trusted setup, which means that you can just generate your CRS. We'll talk about CRS later. You will generate like your secrets, your stuff. You do a trusted setup once, and then you can reuse the same thing for any program that is that is compatible with the proof system essentially. Yeah, so that's why we are mentioning this here. That's why we talk about this specific thing. In this case, Graph 16 requires a trust setup for every R1 system, for every program, or for every circuit. Okay, that's what you will hear as well. So, what is in the setup phase? Well, in the setup phase, essentially, you generate something called a CRS. You also hear CRS. You might also hear something called a SRS, structured reference string. They are, from my knowledge, the same thing. Essentially, a bunch of values that you need. And what are these values, right? What are CRS, right? In this case, CRS are pretty simple. It's essentially, well, this, right? So this is a bunch of stuff, and well, look at the comma. So it's like G1 L to the power of alpha, G1 to the power of beta, G1 to the power of delta, and then G1 to the power of tau 0 to some number, so degree T to -1, degree T. This T is actually I believe it's the degree of polynomial, if I'm not wrong. Might be wrong. But yeah, so and then there's also this value, which is G1 to the power of B times A plus A times BJ plus C. Okay. So these are also the A, B, and C in this scenario refers to the QAP A, B, and C. Okay. Um, and also this is divided by gamma, this is divided by delta, sorry. And yeah, and then this, right? These are all values that you compute on top of your group. So this is computed. So CRS G1 is computed on the um, G1 group, and CRS G2 is computed on the G2 group. And notice we compute a lot more from the G1 group than the G2 group in this specific case. Okay. So there's also a mention of the simulations trapdoor. which is alpha, beta, gamma, delta, and tau. And so let's talk a little bit about what these are. These essentially are secrets that you choose during your setup. And these secrets, we call them the simulation trapdoor, but you may know them as toxic waste, which means exactly what it means. They are things, these are values that, if known by, well, if known by anyone, in this case, if known by any malicious actor, you can create a fault proof. That's why we call them toxic waste. So yeah, and these values we use to essentially, well, to a certain extent, we use it to add security in our protocol itself. To put it very simply, these are all values we use here so that we can make sure that we can use. So these values we've put them here so we can essentially use them to compute compute our result later on, or compute our polynomials later on, without having to reveal our witnesses in this case. Yeah, and these values are only known to the approver, or more accurately, they are only known when it's first setting up. And again, as I said, because these are toxic ways, we usually have compute these values using MPC, multi-party computation, where everyone contribute a piece of secret and then we combine them into this. In that case, as long as one of the parties dispose of their part of the secret, it's secure, right? Of course. Yeah, so there is a sense of trustedness in here. So that's why trusted setup. Okay. Yeah. So here we also call T tau a secret evaluation point. And tau essentially allows you to compute and evaluate any polynomial at the point of t without knowing tau itself. That's why we also call this powers of tau here. So we call this entire thing the powers of tau. We also use this quite often. Yeah. So yeah, that's what is true. This is an example. We have this QAP from previous chapters for the tree factorization problem. This is the QAP, and then we essentially have this as our simulation trapdoor. These are all the secret values. Okay. This is an example, by the way. Don't we usually would not use this. We would not use something that are easily memorizable for our simulation trapdoor, and usually because in production we'll use a relatively big group with a big order, these values are very hard to remember anyways, right? And usually we also wouldn't really save it anywhere again, MPC and all. So yeah, so here it's just showing you that given your QAP, and let's say after you compute your common reference string, and then you compute a common referencing like this, right? And then you can compute actually, yeah, there you go. So this is a common reference string for the BRS6613 torsion group, based on G1. So you need your QAP to actually compute this. And yeah, G2, similarly, you need to compute this. And with these two, these are public, right? So by publishing this, you do not reveal anything about the secret values. You do not reveal anything about your witnesses. I mean, in this case, there's no even witnesses or instances to talk about. This is just the circuit itself. But yeah, you don't reveal your secret values that allows anyone to generate a fake proof. And these are things that will allow you to do calculations and do your proving and verification job later on. Yeah. So what I'm talking about is essentially, let me just show you. So in each phase, okay, let's go through this. So setup phase, you requires a R1CS, you generate a CRS and a simulation trapdoor. Again, these usually are not really used in production. There's also a proof phase where you're given a RNCS, a CRS. So here RNCS usually is in the form of QAP at this point. But yeah, RNCS, CRS, which is the common reference string, INW, instance witness. Recall what instance witness are. Instance is a public value, witnesses are the private values, private inputs. Yeah. So we generate a proof pi. Verification phase, the verifier will have a verification a function that accepts the RNCS, the CRS, the instance, and the proof. Note, no witnesses, because verifier cannot know about witnesses. They are private. So yeah, with the proof and the instances, we are public, and the CRS, of course, you need circuit information to know that what you're computing against. With this, you can basically verify if your proof is correct, if this is correct, right? So you will accept or reject. And finally, simulation, right? Simulation. This essentially, again, this is an algorithm that basically given R, the trapdoor, or the toxic waste, the CRS, and the instance, you can generate a fake proof without knowing the witness. In which case, so in the correct way, you only can generate a witness, you can only generate a proof if you have a witness, right? In this case, yeah, given your secret value, this is to show that I can generate a fake proof if I know the toxic waste. Yeah. Okay, so yeah, that's essentially what it is. And in your set phase, you are generating your CRS and your trapdoor. Yeah, just slowly scroll down. Yeah, here is showing you that essentially, given you have your CRS, you can actually evaluate polynomials, right? Because so here, look at this, okay? A to T G1, right? A to tau T G1. This is the point evaluated at tau. You can see that A to tau expanded is this, right? And doing this product with G1, if you expand it, is 6 times tau G1 times G1 plus 10 times tau 1 G1 plus 10 times tau 0 G1. And tau 1 G1 and tau 0 G1 is known. Why is it known? It's known because it's in part of the CRS. But by knowing tau 1 G1 and tau 0 G1, you cannot get tau 1 or tau 0. You cannot reverse compute it because of its what's it called? It's a discrete log issue. It's a discrete log assumption because of discrete log assumption. Yeah. Um, but here, if you look at the CRS definition, let me just take a picture of the just for you to be able to see it. Give me a moment. Yeah. Okay, let me just do this. Oop, oop, oop. There you go. So given this, let's go up here. So yeah. So tau 1 G1 is here, right? You know it from here. Tau 0 G1, you also know it from here because it's 0 to some degree. So in this case, because here, recall when we are computing it um, for the tree factorization problem, we are actually computing everything here. So looking at this, look at here. So this is G alpha, G beta, G delta, GT0, GT1, or G tau 0, G tau 1. And then this is this, right? And then these are these. Again, four values. And then here, in this case, four values because it's to M, essentially. And here, which is this, right? Okay. And so that's why we can compute this. We can just substitute it in. You see this a lot. Because, well, we want to be able to compute something without revealing our toxic waste or without knowing the toxic waste, and this is how we do it. Yeah, and you'll be able to evaluate this polynomial essentially. Same here. Yeah, that's what CRS is good for. CRS is very, very useful so that when we need to evaluate something, we want to evaluate polynomials, it's pretty easy to do. Yeah. Anyways, okay, so here is just showing you how this will look like in Snark.js. So I'm going to skip. Before I continue, I'm gonna get some water. In which case, any questions so far? Okay, I'll take that as a no. Okay, so let's go to the proof phase. So proof phase, we call proof is essentially it's a function that accepts R, CRS, I, W, right? And, the R1 CS, the common reference string, the instance, the witness. And so yeah, in this proof phase, you'll essentially start the proof generation, right? You have some statement you want to prove, and here is where you do it. And yeah, so yeah, I'll go through this a little bit. There's some polynomial h that is in this form, and you want to do h times t. T is your target polynomial. Divide by delta, and then put this as the exponent of a generator. So G1, so this one, yeah, thank you. It's here. And then you can use your common reference string to compute part of this. So because you are computing this with on the point of secret evaluation, you can compute this by again substituting, right? Your H0, your T0 out, and this is known. And so after this, there's a sampling of two random elements RT, and then we'll essentially compute the curve points. Again, these are known. We are computing this for witness variables. This is known because so more like this entire thing is known. G1 to this power to G1 to this is known because we computed it in our common reference string, and we'll get essentially this, right? GA, GB, times G delta. And yeah, a lot of this we can get it from the common reference string AB. These values are from the R1CS. These values are referring to polynomials in our R1CS. Yeah, so after this step, this few step, we start to generate our proof. And to generate our proof, it's in the form of G1A, G1C, G2B. This ABC is no longer referring to the R1CS. This is the portion of the proof. So here essentially how do we generate? So the proof, let's say for example, this is an example, right? Your proof polynomial, associated polynomial with instance and witnesses is this. And yeah, you'll do the calculations, get some value, and then start generating your points, witness, and your witness here. And then we'll start generating A, B, and C. So yeah, it shows you how it's done here. This is an example on the tree factorization problem for the group of orders 13. Yeah, but essentially here, you'll do the calculation for both A, B, and C, which is part of the proof. I'm just going to quickly walk through it. And here, okay, so here what we need is actually G2. We are not using this, but we are calculating this for our C here, where you can see, yeah, we are using B times G1 or B G1 to the power B actually. So yeah. And with that, so with this actually, so we need to generate the three portion with A, which is generated like this. I'm not gonna talk like go through this in terms of a single and single, but it's essentially the cross product of this, and so on, right? W2, W3, W4, and then this, right? Of course, if you have more than 4 witnesses, it will go longer. It can go longer, right? There's also instances, right? If you have more than one instance, it will go longer. Same goes to B. Same goes to C. Okay. Yeah, so with this, we can then generate a proof which is consist of A, B, and C, or in this case, A, C, and B. Okay, so B is this one. Because this is actually the result from group two. Sorry, from group two. This is the result from group one. That's why you see this, right? Recall group two, I believe it's an extension field. It's an it's an extension group, if I'm not wrong, from previous chapters. That's why you see these V values here. Yeah, it's torsion group, I believe, to be more accurate. I might be inaccurate in this, but yeah. Anyways, so yeah, so this we get a proof from this calculation. A lot of it that we want to calculate. So let's say, for example, like if we want to evaluate the circuit itself, on some points, when we calculate the values, we can very easily just use the common reference tree as shown here, right? So with this tree value, we can now share this proof to any person who wants to verify it, and then they can verify it. Okay. Yeah, that's why I believe you can see this very clearly if you use circom. The proof that generally usually consists of three parts: A, B, and C. This shows again just how this looks like in Snark.js. Okay, that's essentially everything about proof. It's pretty quick in this case because well for those who are interested, I would highly recommend try to implement this. Because they actually do it, they actually explain this in a very compact way in this book. Maybe we should go through it in another session or workshop where we actually try to implement this, or we go through another book that goes a little bit deeper into each part of this prover process. But yeah, here they go through it very quickly. They just talk about the steps like very quickly, A, B, and C, you know. So yeah, yeah. Okay, so verification. Verification essentially, recall verification again here. Let's go back to here. Verification, we take in a few things as an input. Let me just go here. Yeah, there you go. R, CRS, I, and pi. The proof, instances, CRS, and R1CS, or the program. So, yeah, so there's an assumption, of course, that each verifier can compute the pairing map efficiently and have access to CRS. So yeah, your CRS usually is shared. So without the CRS, the verifier is not able to produce or able to verify anything. So that's why you usually will share your CRS, right? Um, yeah. So this to verify, it checks pairings. It just does pairing check, and this is efficient. It's usually very efficient. That's why people use ZK proof to like when you generate a proof and you can verify everywhere. It's very cheap to verify. You can use it for kind of compression purposes when you send messages to a certain extent. This also means that to verify the fact is very easy. So everyone can do it. You don't need to rely on a big fat computer, and that adds some um, trustlessness to things that you integrate this with. Yeah. Anyways, um, you essentially need to verify this, right? Recall pairing checks. What it does is essentially when you do a pairing check between 2 points, it makes sure that yeah, if the pairing check is true or if this track is if the left hand side equals the right hand side, you accept the result. If it's not equals, you reject the result. So yeah, that's what it is, right? So this pairing check essentially checks your proof to see that if it's correct based on so your instance, your secret toxic waste, and your proof, right? Okay. So essentially, well, you can think about it like here, right? It's doing this check. So EAG is this, E alpha beta is this, EI gamma is this, and then EC gamma is this. And if you look here, they they are all also they are equivalent, right? So 108 should be equals to 30 plus 16 plus 36, I believe. Yeah, so it's a times this plus, so 30 plus 16 plus 36. I think nope. Wait, nope, it's not. Let's see, 30, 66, 70, 82 actually. But that's interesting. I might have gotten this wrong, but it should be equal actually. Yeah, this should be equivalent, and times in this case equals plus. So yeah. Not sure it's not equal. But anyways, yeah, this should be equivalent to this times this and this, right? Yeah, there you go. It's equals to 4, and this is equals to this, which is equals to 4. Yeah, actually it's equal, because this is not in a, let's see. I think this is after modular 13 arithmetic. Yeah, or modular, yeah. You modular 13 arithmetic this and it's the same. Yeah. So that's why since the left side, this 1108 mod 13 is 4. And in this case, 82 mod 13 is 4. And both of them are equal, so this pairing check pass, so you can accept the proof. Yep. So verification for a pairing-based proof systems usually are just pairing checks. Yeah, that's it. That's all about verification. Um, yeah, it's very compact again. For those that really want to know practically how this works, implementing it is the best choice. I've seen some of you have submitted PR to the repo that I've shared. Um, I've gone through some of them. I haven't finished reviewing another ones of them. And yeah, thank you for those who actually submitted PR. Thank you for submitting. Feel free to submit even after this class. Yeah, I will continue looking at them after this as well. Us and talk about it in a group as well. Yeah. Okay, finally, proof simulation. So proof simulation is just to show that with the toxic waste, you can actually generate a fault proof. And yeah, it essentially show you how it's done. So with this, you can generate, because you know what alpha, beta, gamma, delta, and tau is, you can create a situation where, or you can select values where you can select values in which you do not know the witness to generate something that works for the verifier. So it's essentially just algebra in this case. I think they show it here. So yeah, we given I equals 11, you can just choose arbitrary elements A and B and then compute it so that it's this, right? And in this case, when you verify this, it will be valid because you just essentially need to, well, as long as you can compute something valid, in this case, right? The verifier will verify as correct. And you can make it valid because of the secrets that you know from toxic waste in this case. And this is valid because of that. You essentially, if you know your secrets, you can essentially do this, right? You can essentially generate something fake. And yeah, I mean, as seen here, right? So let's see. Let's go through this entire thing. Let's try to go through this entire thing. So okay, forging can use simulation trapdoor in combination with QAP and two arbitrary fluid elements from Scala F to compute G1C, for instance, I1. So yeah, because if you know delta, we can compute this times this times this. This is known actually. Yeah, so the main point is A and B, we can select ourselves. Um, and this is computable because we can choose A and B, right? This is computable. We can just make it that it's computable without knowing the witnesses. Recall originally, looking at the prover, let's look at prover. We need to do this, right? We need to compute this. But well, in this case, we don't know delta or tau, right? And so we cannot, because we don't know that, we cannot just choose random stuff because everything here, or like more like later on when we use this as calculation, if we choose something random here, as values instead of doing like an evaluation, right? Um, we might create values that does not pass the verification. But in this case, because we can choose and we can just look at what the result is, um, right? We can use it. We can just choose values that will satisfy the equation, and then we can forge a false proof. Yeah. So yeah, computation driven halving assumption makes G1 times alpha beta from G1 A alpha, G1 beta infeasible. And this is very important because of again, right. So this essentially, if you look at the setup phase, we can only do calculation based on like for these values. We don't know alpha beta. But if we know alpha beta, we can change it up so that in the prover stage, right? Let's look at this. I don't think they have like a full thing here. Um yeah, not this. Is it this? But because if we know that, we can just do this calculation, and then it's very easy for us to compute G1 and C. Yeah, and this will be valid. If you verify this, this will be valid. But it's not actually a false proof, a forged proof. So again, one more thing. So why is it possible to generate a false proof in the first place? Because proof system, this graph 16, and I think most proof systems are probabilistic. There is a very high chance, as in probabilistic, as in there is a high enough chance that your proof, if it's correct, your proof will be accepted, and if it's incorrect, your proof will be rejected. There's a high probability that it's true. There's a very, very, very small possibility that you can generate a false proof out of the blue. But if you have the secret values, you can now do that. Because if you don't have the secret value, it's very hard for you to compute, or very hard for you to compute anything from the group itself, for the cyclic group itself. Um, there's a high chance you cannot reverse compute some value um, from the group into the value of what the actual value is. Yeah. And that's why it's hard, right? And if you want to go through that, it's usually it will take more longer than the time we have in our universe. Of course, not considering quantum computers, although that's quite some time away. But yeah, so it's a probabilistic protocol. Okay, so that's something that is quite important. So I think that's it. For those who are interested, please try implementing it. Make a PR to the GitHub repo. For those who have more questions, you can ask me via PM, private message on Telegram or another platform you may know me from. Uh, you can also ask in a group, so we can all learn together. Um, Here, I think a lot of this is actually unfortunately very much compacted. So if you are interested in a little bit more detailed explanation, um, you can just say in the group, and we can try to arrange either a workshop to go through a little bit more detail in what this is doing. This is a good example actually. The examples are pretty okay, but you need some time to actually go through them to understand why it works, right? Um, yeah, if you want that, yeah, do tell me. But otherwise, if there's no questions, then this is the final session. Oh, well, I guess there's no questions. Thank you very much for coming for this 8 weeks or so. Um, yeah, thank you very much. See you guys next time. in another session. And for those who are interested in looking at the recording is actually available on ETHKL's YouTube channel. Go check it out if you want to go through what's there. You can also subscribe if you want to see more videos that we might record in the future. Yeah. Thank you very much. Have a nice rest of the day. Bye bye.